All right, let's go ahead and get started. Any questions about due dates or anything? I know that I made a pretty big change over break. Anyone can consider where we are, where we're heading?
Is it going to still be on the same material?
Yeah. So I'm going to go from chapter 2.4 to all through chapter 3, and that's it. So what we're going to do this week is going to be covered on the following exam, but not the one that's going to take place next. So next exam is the 23rd, which is over the sections I just mentioned. Then there's the mastery test the Wednesday after that, which is basically I give you 20 functions, you take 20 derivatives, and pretty straightforward. Not that the derivatives will be straightforward, but the format's pretty simple. So Monday just as I promised, on Monday in class we'll have a review session, and then I'll probably also have one over Zoom on Tuesday night. Anything else? I will open up that web work that's due tomorrow night. For people who didn't finish it, I did not mean for it to close, but yeah, it's due tomorrow night. I also put a quiz up today that's due on Sunday, but so usually when I put up the quizzes, like you can't really finish them the day I do them. That one you can. We've covered all that stuff, so you should be able to do that one whenever, and it'll be a good review for the test next week. All right, so we're going into chapter 4. Chapter 3 was pretty much how to take derivatives of lots of different kinds of functions. Chapter 4 is now we're going to take those derivatives and, figure out, use them in the situations where they're useful. So one thing we're kind of marching towards is this idea of optimization. Basically, pretty much every problem you're ever going to solve, engineering otherwise, is going to be one of, I want to find the best solution given the fact that I have some kind of limits, I have some kind of constraints. So, what's the maximum acceleration of a spacecraft? You can't just make it go as accelerated as quickly as you want. You have limits based on raw materials and mass and stuff like that. What's the largest size TV I can put in a room and still be able to see it? You don't want to put a 120-inch TV in your dorm room. It will just never look good no matter where you are. How many customers should a business have every month to maximize profit? And that's one of those kind of counterintuitive things. It seems like it's like, well, I want the more customers, the better, right? Well, after a certain point, it stops being good for you. How can we maximize the efficiency of an array of solar panels? So things like that. I mean, those are the kind of things that we're not necessarily marching towards in this class, but as most of you are engineering majors, those are the kind of things you're probably going to be exploring, whether it's at ASU or wherever you end up next. So kind of working up toward that, trying to find the best solution, usually trying to find the maximum or the minimum something. So looking at this function over this domain from -1.5 to +1.5, without me really explaining to you what these things are, what would the absolute minimum and the absolute maximum be for this function?
2 and 2.
So the absolute max is what?
2.
Why?
Because at the very far on the right side, which is where we're calling the function, the max is at the point 2.
Okay, so you're going off the y value, right?
Yeah.
Okay, we okay with that reasoning? Yeah. I really haven't told you what this thing means yet. Also, I don't think it's quite 2.
It's like almost 1.9. It's close.
It's close enough. Let's calculate it since I know what the function is. Should be a lot more than 2. I don't even know if this graph doesn't even seem like it fits that. Let's just go with 2. I don't even think that works. It's 1.5 cubed is a lot more than 2. So whatever this function is, I don't think it's defined by that, but let's go with 2. So following that logic, what would the absolute minimum be then? -2? So how do we feel about both of those ideas? Okay, and one thing I want to point out, it sounds like, unless there are protests, it sounds like we're kind of keying into the Y values, right? Okay, so those are indeed what the absolute maximum and absolute minimum are. So given some function over some interval, I want to know where the function takes the highest value and where it takes the lowest value. And that is indeed where I'm looking at the Y values in those cases. Any questions there? Right, so definition. So if I let C be some X value in the domain of a function, some input value, then f of C is the absolute maximum if f of C is bigger than, not bigger than, but greater than or equal to f of X for all the X in that domain. So if we go back, and I don't want to necessarily go back, but I think f of 1.5 was our maximum, right? The far right end of that function gave the largest value of that function. So that's our absolute maximum. Again, it's the absolute maximum, when we talk about that, is going to be whatever the Y value is, whatever the output value is. Absolute minimum has a definition that I probably just copy and pasted because it's so similar. What's the only change there?
Less than or equal to.
Yeah, just flip the inequality operator. So it's the absolute minimum if, f of C is less than or equal to everything else on that range. So another term you're going to hear a lot from me, the book, and your web work and stuff. These are called the absolute extrema. Which, if you're talking about both, the collected sets of the minimum points and the maximum points, those are called the extreme points, the extrema. As opposed to absolute, you might also hear the word global. So global max, global min mean the same thing. So I looked at some kind of a surface example and talk about some vocab here. Any questions so far? So let's focus on absolute extrema first. So we know we can have absolute min and absolute max. Don't have numbers really, but I think that's okay. What is the absolute minimum of this function here? F of A. Okay, I think I agree with that. So F of A will be the absolute minimum. How about the max? F of D. All right, and these new things. So again, I kind of want to see what we all think before we formalize this, but local minimum. So remember the absolutes, we can also call those global extremes. How about the local minimum? So I got to vote for F of C. Why? So why are we saying F of C?
Because I'm guessing that local extreme is the same as like relative min and max.
Okay, so what's a relative min?
It's so like when you're thinking of a graph that has like infinity and negative infinity, then the relative mins would be the ones that you can actually reference and not have to say infinities. Like, so that point is relative.
This is one of those weird things like,
Oh, we need more information.
you ever heard the old judge named Potter Stewart? It's like someone asked him to define something. I can't remember what it was, but he said, I don't know how to define it, but I know it when I see it. I kind of feel like you're in that boat.
Yeah,
right now.
I don't know.
So I'll tell you, yes, this is a local minimum. But can anybody articulate why right now? What changed from negative to positive? So the slope changed from negative to positive, right? So
Then why is it not F of E?
why is it not what?
Why is it not F of E?
It might be F of V. So let's go back to absolute. So let's look at absolute minimum. Does it make sense for there to be two things called an absolute minimum?
No.
Well, let's say this. You can't have two absolute minima. But if you have two absolute minima, what do they have to? What has to be true about them?
It's the same.
That they're the same. So you might have a function that reaches some minimum point a bunch of times, but they're really whatever that y value is unique. Can I have more than one local minimum? So in this case, I'll tell you yes. That is f of c and f of e.
Is this assuming like this function goes to infinity and negative infinity?
No, in fact, I'm actually just assuming. What's the domain of this function that I'm assuming?
A to x.
A that mean whatever the point, whatever the far right point in this graph is, right?
Yeah.
X is just a variable, but yeah, so from A to whatever that rightmost point is. So no, in general, we don't assume these functions have like all real numbers literally. We can sometimes, but for this, we're not. In general, we're not making that assumption. Back to the idea of a local min. Isabel was talking about the slope being negative and positive on different sides of f of c. So over here, if this function right here is f, what's the function that tells us about the slope over here? Or over here, or anywhere? F prime. So over here, I can say f prime of x. Give me more room. What's true about f prime of x over here? And over here, yep. So that is one valuable way to look for local mins and local maxes, is that on one side you have the first derivative has one sign, and on the other side the derivative has the other sign. Is that thing also true around E? Yeah, I think in the same direction too, right? Okay, so we have local mins at f of c, f of e. I like the way we're thinking about how to find them. Where are the local maximum points? D and B. F of B, F of D, anywhere else? Okay.
Is f of a also a local minimum?
F of A is not. So I see why we would think it is, but the definition I'm about to give you will point out why it can't be. For the same reason that whatever that rightmost point is not a local maximum. And I'll explain why that is in a second. Is that your question?
Does local maximum and local words minimum have anything to do with differentiable stuff?
They could.
Because C, they're all gonna ask about C type on it.
Is my function differentiable here? Is it differentiable here?
Yes.
Okay, so I think that right there tells us that I can have those local extremes at places where the function is not differentiable, but it might be differentiable. You said over here the function is differentiable, right? What's the derivative at the local minimum? Well, we said it was negative here and positive here, right? Can we say anything about what it is here? It should be exactly zero. So this derivative exists and is zero. This derivative doesn't exist. So we can't have local mins and local maxes at places where the derivative doesn't exist. If the derivative does exist, do we think it has to be zero?
Yes.
Okay, I got one vote for yes. We'll visit that later, Jared.
And then for f of d, that can be both the absolute max and the local max.
Yeah, they can coincide. That's another thing. That's another good thing to point out is they can absolutely coincide.
So the maximums can coincide, but the minimums cannot.
They might. They just don't here.
Okay.
The absolute min here is not a local minimum.
Because it's an endpoint.
Okay, so let's see if let's hold that endpoint thought and see if we can generalize that. So let's put some more formality behind that. So talk to you about absolute extrema. How does that relate to local extrema? So again, very similar definitions for local max and local min. If f of c is greater than or equal to f of x when x is near c. Now I'm not saying anything about the whole domain. I'm just saying about, you know, I know that is vague to say near. We'll talk about what that means in just a bit, but for now, If f of c is bigger than everything in this vicinity of c, then that's a local max. Similarly, if it's the least of all the things in this little window, it's a local min. So what does near mean? So this will go for both maximum and minimum, but just kind of wanted to spell out for one of them. If you have f of c, so if you have a local maximum of f of c, then there's some positive number, just one positive number. So let me just draw a picture. So this right here is going to be the point C f of c, right? Basically, can I pick like some number epsilon where I can have like a window on either side where f of c is the biggest point there? Really, I have lots of options. Let's just say that epsilon is, you know, if this point is c, I can call this point c plus epsilon and this point c minus epsilon and kind of bracket off this function there. Is f of c the largest thing in that little slice? So if you can pick a number and kind of make a window like that, as long as your point's on the center of it, then yes, you have a local extreme point. By that definition though, why can't I say that f of a is a local, was it min or max? Yeah, why can I say that why can I not say that f of a is a local minimum?
Because it doesn't have an epsilon minus.
Right, so once I try to like open up a window around that point, I've left the domain that I actually care about this function. So for me to build that interval around this point doesn't make sense for this function. Whereas around here, it does. Or around here, it does.
So epsilon just some, like, epsilon literally just means like near. Like,
Yeah, I mean, the word near is fine for most of what we're gonna do. I just wanted to kind of give a rigorous formal definition of it to kind of give you another way to look at it. But around E, like, I can take whatever this distance from here to here is and cut it in half and call it my epsilon. Or cut it in thirds, whatever. It's so long as something exists that you can do. Any questions about that? So we got absolute minimums, sorry, absolute extremes, local extremes, how to find them. Now let's talk about where to look for them. And a lot of these ideas just came up, but let's kind of tie a bow around it. So on this graph, where do we have to, so if we want to look for, let's look for locals first. And what I'm asking here basically is, where might local extrema be? In general, what I mean is like, what kinds of points are local extremes going to exist at? Like a point like this, where the derivative is positive over here and positive over here. Could a point like that ever be a local? No, doesn't make sense, right? If you're increasing the whole way through it, then something in the middle is not going to be an extreme. So having said that, what kind of points are you looking for? So one thing we can look at is where f prime of x equals 0. Let's say that's the only thing we were looking for on this function. Would that have gotten us all the local extreme points that actually exist there? Yeah. We would have missed one, I think. I think looking for the points where the derivatives equal 0 would have got us f of b, f of d, and f of e. Why not c? Right, so the derivative does not exist at c. So if we're looking for points where the derivative is equal to 0, what else should we look for? Limits? Limits of what?
the limit of like f of c.
That alone won't tell us much because it's continuous at C, so we know that since the function is defined there, the limit will exist. But what can we say about f prime at C? Doesn't exist, right? So those are those are kind of the candidates for where your local extremes might be, where the derivative is equal to 0 and where the derivative just fails to exist.
So real quick, so how do we know that the derivative is not going to exist?
So I'll give you a couple ways to think about this. One, since we're looking at a graph, we've talked a lot about derivatives being the slope of a tangent line to a graph, right? So if I were to draw a tangent line around f of d, I really only have one choice, right? It's going to be horizontal. Is there a way for me to draw a line that only touches that point FC once? I mean, I could do it lots of ways, right? Which means, you know, the limit that defines that derivative doesn't really exist because I just gave like 3 different values for it. So it could be any of those, and it could be an infinite number of things. So because I can't like pin it down, that limit doesn't exist. I'll go ahead and answer it another way when we actually like look at like algebraically defined functions. It'll become more clear why the derivative wouldn't exist when you're actually looking at, you know, some formula. You can figure out when those things don't exist. Anything else we need to look for local extremes? So those are basically it. Either the derivative is going from positive to negative and it must go through 0, or it's going from positive to negative in some direction and the 0 just doesn't exist. How about for absolute extrema? Where might those be? Is it possible for absolute extrema to exist wherever local extrema are? Okay, so absolute extrema can exist, you know, with local extrema. Did we see examples of that on this function? Right, so f of d was an absolute max and a local max. Was that the only one that was both? Yeah, it was. But if we were trying to find the absolute extrema and we just looked at wherever the local extrema were, we would have missed some stuff, right? So what else do we need to look at? Then we can look at the endpoints as well. And that's basically it. So local extrema can take place where the derivative is equal to 0 or the derivative fails to exist. Absolute extrema can take place at either one of those two things, but they also might take place at. Did we say that this was a global extreme? So this is a global minimum. That one's nothing. So I mean, these are the things basically you have to check. A lot of these things are not going to necessarily be true all the time, but these are the things you kind of have to look at. And since you're looking at a domain of infinite numbers of x values, you have to be able to narrow it down somehow. Any questions so far? So let's find the local and absolute minima of this function x squared. And for this, I wasn't doing the domain all real numbers, but let's do this. Let's do a domain from -1 to 5. So I want to find, what do you want to do first, the local or the absolute extremes? Actually, I just want minimum points.
Extreme.
Absolute, okay, yeah. Extreme doesn't narrow it down. So I want to find the absolute minimum. So where would I need to look? So definitely need to look at the endpoints, right? So f of -1 and f of -5, or sorry, f of +5. What are those? One? 25. I think I can say no to that one right now, right? Okay, so it could be -1, 1. Can I say for sure that it is? No. So I look at the endpoints, but what else do I need to look at? Need to look at the locals, right? How do I find the local minimum? So local minimums have nothing to do with endpoints. What do they have to do with? Slopes. So how do I start dealing with slopes, Isabel?
Take like, I had it's square, it will just go for that whole. But there's gonna be like more.
So let's make sure. So we have an intuition, right? So we think the absolute min is equal to 0. So we have a suspicion about that, right? So let's make sure that it is. How do we find local extremes, either minimum or maximum on a function? Got to find f prime, right? So f prime of x equals 2x. And I want to think about this two different ways. I want to set this equal to 0. If 2x equals 0, what does x equal to? All right. So I know that I'll have some kind of local extreme where x is equal to 0. But now I need to look at what the function is doing at that place, which is f of 0 equals 0. So that kind of confirms our suspicions even more. We took a derivative. What else do we need to look at with the derivative? Where it equals 0 and what else? Or what?
You're talking about the f prime where it doesn't exist, right?
Yeah, where it doesn't exist. So the derivative is 2x. Does it make sense for that not to exist? No. So that derivative 2x, that's a polynomial. It's a straight line. It's defined everywhere. So we found the only point where the derivative is equal to 0, and we can see that it's going to exist for all x. So now, because of this, we have a third candidate. We have f of -1. We had f of 5, which we already threw out, and 3, f of 0. So those are basically your three choices for what the local minimum, or what the local, absolute minimum. So which one of those is the absolute minimum? 0. So indeed. How many options do we have for local minimum? That one. That's the, so we found 3 candidates for the absolute minimum, but really the only local minimum that could exist is f of 0 equals 0. Any questions there? All right, how about this thing? Let's find the local and absolute max of sine of x. And I'll just do the standard 1 period 0 2 pi domain. Right, so what do we want to find first? Let's find a local. So find local extrema. So if I want to find those local extreme points, what do I have to do? f prime of x is equal to
Cosine of negative or cosine?
cosine. All right. Is there anywhere where cosine of x is not going to exist? No. So the domain of cosine is all real numbers. So we're not going to get any of those points, but are we going to get any values where x or cosine is equal to 0?
Yeah.
So where is the cosine of x equal to 0? Here's my unit circle. What?
Pi over 2.
Pi over 2 is one of them.
3 pi over 2.
3 pi over, that's a good circle, and 3 pi over 2. So yeah, remember the on the unit circle, what coordinate of the points on the unit circle gives you the cosine, x or y? X values, right? So pi over 2 and 3 pi over 2 are the y-axis crossings, so x is equal to 0. So yes, I have pi over 2, 3 pi over 2. Is it possible for both of these things to give me a local extreme point?
Yeah.
Okay. But if they both give me a local, oh, I just want maximum, right? Let's change this word. Let's find minimum and maximum. They're not really that hard to find both. So I have these two candidate x values, pi over 2 and 3 pi over 2. How can I find, how can I keep investigating where these local extrema are?
I have to set those values instead of the original function.
Yep. So remember, like, one of the first things we talked about was, and this came from you, not from me, that when you're looking at any kind of extrema, you're looking at y values. So if I want y values, I really need to go back to my original function and plug in these input values. What is the sine of pi over 2? That's equal to 1. What is the sine of 3 pi over 2? Negative 1. So can we say anything right now about local min, local max? How many candidates do I have for local min and local max?
Or one of each.
I mean, well, I have two candidates for both, right? But one is clearly bigger than the other. So this is the local max. And this is the local min. Now think about what you know about the function sine of x. Is it possible those are actually also the absolute? Yes. It's very possible, right? But what other points should we check just to be sure? Check the endpoints, right? Check the endpoints of what is f of 0? And what is f of 2 pi?
Sine of 2 pi is 0.
Yep. It's one full rotation. How many rotations is 0 radians? So 0 and 2 pi are, they're coterminal angles. They're going to have the same sine value. Does it make sense for either one of those things to be the absolute min or max? No. 0 is smaller than the, so we already know of points that are bigger than 0 and points that are smaller than 0. So neither one of these things is an absolute max. But there has to be an absolute max and absolute min. So where are they? Garrett? Yep. And again, just pointing out that you're not guaranteed to find, I mean, you're not guaranteed to find absolute max or sorry, absolute extremes and local extremes at any of these points, but these are all the things kind of you have to look for, all the places you have to look for. Any questions about this one? So let's think about something here. I want f to be a continuous function defined on some closed interval between two real numbers a and b, whatever they are. Does f have to achieve a minimum and maximum on that interval? What I mean by that is, like, is there an absolute maximum and an absolute minimum? Does there have to be?
Yeah.
Got one vote for yes, they have to exist. We got some head nods for they have to exist. So a continuous function, think about what continuous means. Closed interval, so my domain is everything between A and B and A and B. We believe those maximum and minimum have to be. So what if I said f is not continuous? But there still have to be do those maximum and minimum points still have to exist if the function is not continuous?
Yes, it would still have maximum.
They still would have.
So we're saying yes on the second one too? Okay. What if the interval's open? So my domain is everything between A and B, but not A or B. Now I got to vote for no.
It still has to.
Still has to have the extremes in it.
As long as the values in the domain have to be at least about highest amount.
So as long as there's stuff in the domain, that means there's stuff in the range. So the max and min have to be in that range. Is that what you're saying?
Yeah.
So are we agreed that all these are all three yes? I'm hearing yeses, but I'm also hearing grumbles. So let's see how we did. So the extreme value theorem. So if you have a function that's continuous on a closed interval, f will have a minimum value. So this is the thing I gave you all kind of like, oh yeah, that has to be true, right? That is true. So if you have a function that's continuous on a closed interval, then f of c and f of b are the absolute minimum and the absolute maximum. And they exist, they are achieved. So you're right on the first one. What about the next two? Does that function right there have a minimum and a maximum?
Yeah.
What are they? What's the minimum?
Well, whatever's right, what 3 point,
Like less than negative,
right,
less than those.
epsilon negative 1.
So this point right here, let's say it's 2. Is the minimum of this function 2?
No,
What is it?
whatever's
Oh,
close.
slightly greater than 2.
How slightly? How slightly?
Epsilon.
What's epsilon?
The
variable.
Epsilon's not, it's not like a constant. I can make that as big or small as I want.
Should we do like a limit or two?
Well, it does have a limit of 2, but that doesn't mean that 2 is on that function. So,
There has to be one.
no, there doesn't. I know it seems strange, but here's the thing: 2 is the minimum value of that function. Are we okay with that idea?
Yeah.
Yeah. But is 2 a value that function takes?
No.
No. So a minimum exists, but the function never reaches it.
But then 2 is not the minimum
It
value.
is. And I mean, and those things sound like they don't make sense together, but if you were to ask me what the smallest value this function can take is, I would say 2, even though it can't ever take 2. So I know those things they're strange to try to reconcile each other, but this right here, this shows right here that if you have an open interval, you might not ever achieve those extreme points. Also, if you have a function that's not continuous, what's the maximum value of that function on the right? Does the function ever reach 5?
No.
No. So you really need this thing. You need continuity and you need the closed interval. And just to kind of one more wrench to throw in here, what's the minimum value of the function on the right? Does it ever reach 0? Yes. So those things might exist. You just can't guarantee them. But if you have a function that's continuous and it's defined on a closed interval, then these minimum and maximum have to exist. And kind of think about the last couple examples. We kind of assumed this, right? I gave you functions that were defined and continuous on closed intervals, and we just went looking for the absolute min and max. We didn't really worry about the fact that they wouldn't be there. They will be there. This is the theorem that guarantees that those will exist. Any questions here? Especially about why continuity and that inclusive interval are really important. Another one, we kind of, and you guys, you all kind of got to this one before I got to this slide. For Moz theorem here, if you have a local extremum and the derivative exists, does the derivative have to equal 0? I think I asked you this like half an hour ago, and we seem to be on board with that idea, which is true. If you have a local minimum or a local max and the derivative exists, it must be equal to 0. Having said that, though, is it possible to have a local extremum and have the derivative not exist?
Yes.
Right. So this thing is not true in reverse. Just if the derivative exists, the derivative is 0. And another valuable term to know here is a critical number. So basically the two things that we talked about where local minimums can be. Let's actually revisit that. When we're looking for local extreme points, where are we looking for local extremes? What two things?
The first derivative equals 0 or does not exist.
Right. So it's where the first derivative equals 0 or where the first derivative doesn't exist, right? Now we're just going to swallow both of those things up and call them critical points. By definition, that's what a critical point is. It's a place where the derivative is either equal to 0 or where it fails to exist. How are we doing? All right.
Oh, so all the points at the local and maximum minimums are critical points?
Yes, so local minimums, if they exist. So I'll say it this way. Local minimums have to show up at critical points. Not all critical points are local extremes. We'll look at an example right now. So I want to find the critical values, the critical points of this thing here. So how would I find the critical points of f of x equals x cubed? How do I get the slope? Right, so I need the derivative. So f prime of x equals 3x squared. And just to make sure we check for it, is there anywhere where this will fail to exist? No. Is there anywhere where it's going to be equal to 0? Where? Is that the only place?
Yeah.
Okay. So f of 0 is equal to 0, right? Is that a local minimum or a local maximum? We don't know yet. How do we find out? I'm going to say the domain is, in this case, all real numbers. By the way, do I need to tell you the domain for critical points? No, domain just has to do with the derivative. So all I really need to do is look at the derivative. So I know that x equals 0 is a critical point. What kind of extreme point might that be? Could be a local min or a local max, right? Do we know yet what that is? How can we find that out? So here's one way to find this out. We'll talk about others later on, but this is probably the most direct. So right here, I'm graphing basically x values and f prime. I know that when x is equal to 0, f prime is 0. So what I want to do now is I want to look at, let's just say -1 and 1. And really, I could choose anything. I just got to choose something less than 0 and something bigger than 0. And what I want to do now is this. I want to look at the derivative on either side of 0, because hopefully that'll give me a clue about what kind of extrema the origin is, 0, 0. What is f prime of -1? 3. What is f prime of +1? 3. So one thing I want to be clear about here is we know the derivative is equal to 0 when x is equal to 0, right? Are there any other places where the derivative could be equal to 0?
It has to be if it goes positive twice, doesn't it?
That's what I'm asking.
On this spot.
So let me ask, so the derivative is 3x squared, right? If there was another place where that was equal to 0, our equation would have found it, right? So I believe, I'm telling you, I know for a fact, that the only place where the derivative is equal to 0 is at x equals 0. The derivative is positive everywhere where the derivative is not equal to 0. So basically, you have a function that's growing to a point and then growing directly afterward, right? Is that a maximum? Is that a minimum?
It's neither.
It's neither thing. So if you don't remember what the cube function looks like, it kind of looks like this. It grows, kind of flattens out, and then it grows again. So at the origin there, what is the derivative equal to? 0. If I were to draw a tangent line to the origin, you would get a horizontal line. So it's a critical point. But is it a local min or a local max? It's neither one of those things. So that's one thing I wanted to point out before we go is that if you have a local minimum or a local max, it has to show up at these things called critical points. But just because you found a critical point doesn't mean you found a local extreme. You can have these things right here, which are neither, and sometimes you'll hear them called a saddle point, where the derivative is 0, but the derivative is 0 at the point, but on either side of that point, the derivative is either positive or negative, not one or the other like you would hope it would be for a minimum or a maximum. Any questions here? Yeah, I don't want to go any further today. We got 1 minute left. So I'll go ahead and stop here. Any questions before we break? All right. I will see you all Wednesday.